Hello, welcome back. Uh, another week, week 7 in statistics. Uh, okay, it's quite a long time to become almost proficient in understanding statistics for you now. I'm hoping you're understanding everything from week to week because from starting from this week, we're building upon what you have learned. Okay, so this week, finally, we're there. We're going to learn how to do proper analysis. Okay, the type of analysis that you see in scientific papers, in technical reports, in statistical related governmental reports. Maybe I haven't seen any of them, but you know. Uh, it's going to be a formal statistical analysis. All right. So I'm going to try to make it easy for you. Uh, Hopefully, we're going to require very little memorizing of the formulas. Regularly, I know very few of the formulas that I teach, but I remember them along the way. Sometimes I have to rediscover them. Uh, for example, this week's formula has a logic on its own, but next week's, when we start doing correlation and regression analysis, the formulas over there, when you look at them, they don't mean anything. Actually, they mean something, but they're hard to remember. I don't remember uh, all of them properly. Like I don't remember the formula for you know correlation coefficients or coefficient of determination, and sometimes even I don't remember the regression equations themselves, but they have a story, mathematical stories mostly, and yes, you can remember those stories, re-evaluate them, and then uh, they're going to come to you anyhow. During you're a lucky class. Uh, it's unlucky that we're together in the classrooms, but you're lucky that you're having distance exams, which means you can have formulas by your side, uh, and that means I'm going to change the way I ask questions uh, to you, because if I ask you calculate variance, you have the formula over there, you have the numbers in the question, so you're going to calculate. There's nothing interesting about it. It's like the primary school first year, second year homeworks. Write the poem in your book to your notebook. That kind of thing. We don't want that simplicity. So anyway, that's some part of the story. The essence of this thing is I want you to understand what you're doing, what we're doing, what statistics is about, what statistical analysis is about, why you do it, how you do it, and most importantly, what information will you get out of it, right? Because you're going to be decision makers. I cannot emphasize this enough. Uh, I will be talking about this all the time. To make a decision, you need some input about uncertain things. Sometimes you expect one phenomena to be this way. Theoretically, it is this way, but you collect data and you see that it's the other way. And we're going to see examples of that today, uh, towards the end of the lesson. So you cannot just say, okay, if this happens and that happens, then this is going to be like that, and I will make my decision based on that assumption. You have to check. Okay, that's why we have statistics, because most of the times history teaches us some things. It repeats itself in a certain way, and if you have a grasp of how it repeats itself, then you could be prepared for making decisions under uncertainty. But sometimes it doesn't. Okay, it's case by case, uh, changes from time to time, and you know you have to analyze. Now, it's good if you have some coffee with you during the courses, because if you're lying on your couch and watching the video on laptop, sitting on your lap, because that's why it's called a laptop. It's not good to have it on your lap, by the way, or watching it from your phone. You could easily fall asleep. Be sitting, have pen and paper with you, because today there's going to be many times when I will ask you to pause the video, solve the question, then resume it again to see if you have done correctly. Okay, it's best you have a calculator with you, by the way. And if you're using a computer, you could just open up an Excel file, and if you're proficient with Excel, uh, you could calculate over there. It helps. And okay, don't just watch. Okay, I watch videos of NFL games. I played American football myself. When I watched them, I said, "Oh, I could have thrown that pass." You cannot. Okay, you have to practice. Or you watch a concert, a live show. Yeah, I can play that solo better. But he's the guy who wrote that solo. You cannot play it better. But even if you can, you have to exercise. You have to practice. And it's the same with statistics. You can watch and say, "Yeah, easy. I understand." But the exam time comes. You see the questions. You see how much time you have, and how will I be able to finish these in 20 minutes? It won't be 20 minutes, but uh, you're going to have 20 minutes left and three questions to solve. And that's going to put you in a pickle. Okay? So practice. Practice makes perfect. So without further ado, let's get going. Let me share this with you. Okay, week 7 bivariate distributions, categorical analysis. So this bivariate distributions thing is going to be a long chapter. It's going to stretch for at least 4 weeks, I guess. Uh, this week is going to be categorical analysis, and the remaining 3 to 4 weeks is going to be numerical bivariate distributions. Okay, so over there you're going to learn the whole correlation and regression analysis thing. Now, if you look at the books, statistical books, this they mostly never call this bivariate distributions, bivariate relationships. They call it uh, correlation and regression analysis. There's going to be a chapter like that. Sometimes it's going to be followed by a multivariate regression analysis chapter. Rarely a nonlinear regression chapter. I'm hoping I could, teach you regular simple linear correlation and regression analysis, and some nonlinear transformations maybe. And if I have time, just using the computer package, show you the basics of multivariate regression analysis. We're going to see how much time we're going to have for what. But in those books, generally, the regression chapter is going to be far away further into the book. It's going to be like chapter 9 or 10. Or, do I have a statistics book here? I don't, because I don't need it. I've got a couple of those in my office, but it's going to be far away in. Uh, and between the introductory part and the uh, regression, there's going to be whole 4 or 5 chapters of statistical inference, hypothesis tests, confidence intervals, analysis of variance, and what have you. Uh, I teach them in the second semester. This way of teaching makes more sense. And if you remember that book that I advised you to read, it also follows that structure. I I didn't learn this structure from Middle East technical statistics. My teachers used to follow the same way those books follow. Uh, I learned this approach from a very special person. So my own Hoja, whom I respect so much, I love so much. He's gone now, may he rest in peace. But uh, as soon as I have seen his approach, I'm like, oh yeah, this is the way to go. So I've been talking for some time, but we still haven't started. Bivariate. What is bivariate? Maybe pause and think about it for a moment. Don't Google, just think. I'll give you a hint. Binoculars, bicycle, bisexual, maybe, uh, and you have unisex toilets in some places, and you have universe, and you have unite, and you have univariate. So univariate and bivariate and multivariate. Okay, so bi is two, simply bicycle, two cycles, and so on. And if our universe was a duality, it would be biverse, two universes combined together. So bivariate distributions are going to be two variables that we investigate together at the same time. So far, we have seen, you know, univariate distributions. They looked like this. You had a variable, you had a frequency here, sometimes probability here. Okay, it doesn't matter which one you have, and you had a graph of the frequencies, sometimes a bar chart, sometimes a histogram, whichever fits. Okay, but now you have two variables, bivariate distributions. It looks very much the same, right? No, there's going to be change to this. That's what is going to change. Instead of having the frequency related to x, you're going to have a variable y over here. So uh, the way you denote the graph is going to change. So each point, okay, this is a continuous graph, so it doesn't make much sense in a bivariate distribution. But suppose if the corners are points, there are points over here, that means each point is a tuple. Okay, we call it a tuple, uh, T-U-P-L-E, tuple. Uh, that's, or sometimes we call it a data pair. Okay, a two tuple would be a point showing that information. So that point would be a point where x is 1 and y is 2. How could I get this kind of information from you? I would probably ask you this. Uh, if I was interested in finding a relationship between weight and height, okay, I would ask all of you to, you know, person by person, tell me your weight and tell me your height. And the first person would say, for example, 170 and 62 kilos. Now that's a data pair, okay? And in a two-dimensional Euclidean space, as in here, it's a coordinate. It shows me a point, okay? Suppose 62 kilos and 175 centimeters, okay? Somewhere over there, something like that. And each point would denote a single person. Uh, so it brings some important issues like, you know, in the univariate case, we just take the raw data and just order them because, you know, that it becomes more readable. Then you can get grouped or ungrouped frequency distributions out of that. And when it's ordered, it's easier to do that. It's harder to get an ungrouped frequency distribution from the raw data. It's much more complicated. Not complicated, but, you know, it's you know, 3 and then 1 and then 7 and then 2. It's hard to get everything in its place, but you can order them. But when you have two variables and each data point has a coordinate, x coordinate and a y coordinate, it's a two tuple. you cannot order them separately, because you cannot break that bond between the two coordinates of a point. Okay, then that would be wrong, but there's time to investigate that. Basic idea, okay, this is a numerical case, obviously. Basic idea is that you have two variables that you're going to investigate together, right? There are a couple of famous bivariate relationships. Okay, we're going to be talking about relationships too. Uh, I had a girlfriend, not that kind of relationships, but similar to that, if you come to think of it. Okay, it's the relationship between two variables. Uh, Sometimes the relationship is strong, sometimes it's weak, and sometimes it's direct proportional, sometimes it's inverse proportional. There's a lot to investigate over there. Anyhow, P and Q, is that familiar to you? Now that you, you have spent 7 weeks in business school, uh, and you're taking economics courses, I presume you have seen some relationships about price and quantity in the economics courses. Let's see. As quantity increases, price falls, or better to say, as price falls, quantity increases. Have you ever seen anything like this? This is a very well-known fact. It's the law of demand. Okay, if the price of a commodity increases, the demand to that commodity falls, uh, or declines, or reduces, or you know, diminishes, whatever you want to call it, right? And when the price falls, you can buy more of it. Are there exceptions? Yes, like given products, if I recall correctly, they're the products which face higher demand when price increases, but they're exceptions. And in statistics, we don't care about exceptions. Uh, when they become majority, they're not exceptions anymore. Then we investigate them. But anyhow, this is a very famous relationship, the law of demand. In many economics books, you're going to see this as a straight line, or a perfect curve that goes like that. I didn't draw it that way because I draw it by hand in PowerPoint that and I couldn't do it perfectly. But reality is more like this. Those straight lines and straight smooth curves that you see in economics books, they're representatives of the general idea. Never ever in real life you see such perfectly straight or perfectly smooth curved patterns. Reality is more like this, and even more distorted than you see here. But the general idea is over there, and the curvature of this could change from product to product, and based on price and quantity, and that in time takes you to alternative products and price elasticity, stuff like that, I guess. So when you're learning economics, there's lots of statistics underneath. um, you could listen to those courses with this perspective, maybe. Another one, what happened? Price increases and quantity increases. Law of supply. Okay, that's the producer perspective. That's what a supplier wants to do. If the price becomes higher, he wants to sell more. If the price falls, he doesn't want to sell much because it's not worth producing. In many cases, again, it's not a perfect curve. In the upcoming weeks, we're going to insert perfect lines and perfect curves into data, but the real raw data itself is not perfect as such. Okay, what else do we have? Inflation and unemployment. How will they behave? They will behave like this, like the law of demand. Okay, this is another famous function from economics, Phillips curve. Okay, what else? Okay, that's how you show it when you have the two-dimensional Euclidean space. Is it better that I y, x. Okay, but sometimes you're interested in dynamic cases, so your variable also has a time component in it, as in this one. Okay, suppose this is one of your variables, and these are months or days or weeks or years, not centuries, because we don't have data for that longer time of period of time. Okay, and this could be your other variable. Okay, so uh, you're trying to understand the percent change in two variables. Do they act similarly? Okay, would be your question. Is it when you're talking about a bivariate relationship? Do they move together perfectly or roughly, or do they have no relationship, or does one go down while the other one goes up, and when that one comes down this one goes up? That means something too, correct? That means they have an inverse proportional case. But if they, this is pretty good to think that the two variables almost have the same shape, same structure, same direction as they're moving. This is another very well-known relationship in economics. It's the GDP and consumer expenditure. Okay, so the blue line here would be the change, not the direct value, but the change in consumer expenditure, and the other would be GDP. Okay, when one rises, the other rises. When one falls, the other falls, and they move together, and they generally do move together. And to understand macroeconomics, you could, for example, try to uh, analyze the direction. What does it mean when this when they both go up, when they both go down? Is it a recession period? Is it something else? But I don't know that much economics, but uh, yeah, they're related. And even when you have a time component, you can do it like this: consumer expenditure and GDP. One could be up, one could be down, but you could show both variables as a single data series by proportioning them and trying to investigate the proportion. So this is consumer expenditures share within GDP. So as you could see, there's fluctuation here. Okay, there's variation, but it has a visible trend going upward. So in time, consumer expenditure is becoming a larger part, is taking a larger part in GDP. What does that mean? How does that happen? Is it a good thing? Is it a bad thing? Should you avoid it if at all possible, or whatever? But as you see, I'm talking about in in the last 5 minutes. We've been talking about lots of macroeconomic decisions, right? Uh, if someday you become the minister of economics, and you know you want to talk to the press every week, know what you're talking about. Okay, there's statistics in economics, and the decisions should be given by following data, following trends, understanding the mathematics behind parameters. Okay, so most of the times we're going to have, in numerical cases, of course, we're going to have this type of relationships. I'm making a general introduction, and I'm mostly making it using numerical data because it's easier to grasp the bivariate relationships by looking at the numerical cases. Categorical data is always troublesome, and today you're going to see that it's relatively very easy to analyze. So first, understand what two variables are, how do they move together or together, uh, not always in the same direction, but together. Okay, and the relationship between the two variables, and then it's going to become you're going to understand the categorical analysis easily. It's best to give the general idea using numerical case. Uh, Most of the times we're going to have something like this. Each diamond. I don't know why I use diamond. That's the easiest thing to draw, possibly. Okay, so you have these diamonds. Each diamond is a point, and it has two components: an x component and a y component. And just look at this and maybe pause the video and tell me whether you think there's a relationship or not between x and y. Do you think there's a relationship between x and y here? Pause, comment. Okay, now you resumed it. I guess so. There seems to be a relationship between x and y because they're very directional altogether. Are they exceptions? Yes. For example, they're generally moving upward together. So as x grows, y seem to grow. But if you take that point and those 2 points, as x grows, y falls in those 2 points. And the same case here, and the same case here, and the same case here, and the same case there, right? Here, there. And almost half of the points show that when x grows, y falls. But we don't care about individual values. When you look at the data set as a general shape, it's going upward. So that's the idea. We don't care about minor falls or rises, but you could denote this relationship using a straight line like that. Better would be maybe to use a curve that passes through these data points in a more explanatory fashion, but straight line, it'll do. This is what we call undirected data. Okay, it's just scattered. By the way, this is called a scatter plot, if you're interested in Excel, for example. If you write xi, put the data, yi, put the data, and make sure that each row is about a single data source. So if I'm asking you your heights and weights, and that would be, each row would be a different person, don't just write them in order within themselves, but write the pairs. Excel doesn't mind if you have orders or not, but write them in pairs. If it's GDP and consumer expenditure yearly data, first row would be year 200, 2020, 2019, 2018, blah blah blah. Each year would be showing you consumer expenditure and GDP of two values. And by the way, if you want good statistical practice, you could try to find, you could find such data in OECD, maybe in World Bank, maybe for Turkey, maybe in Turkstat, and you could look for other sources. And if you could find data for about a country, any given country, you could find for Angola if they provide data. I don't know. Could maybe find it in OECD or somewhere. You could find those. You don't have to have hundreds of points. Start from 2000, the change of millennia, and get the last 20 points, and try to get a scatter plot out of that in Excel. You could simply do that. Just write the data pairs. If you like, insert year as a third column, but select those two guys, GDP and consumer expenditure, insert graph, and it's going to probably offer you to make a scatter plot, or you could just simply pick a scatter plot and draw such a graph. Would be easy. This is the first thing you look at when you're analyzing numerical data, because your eyes are better than you think. They work like a computer package. You look at it and you say, oh yeah, they go up together or they go down together, or there's no relationship here, kind of thing. Okay, this is undirected information because it's just a scatter plot. But if you connect the points with a line, then you're going to get exactly the same data. Okay, but you're going to get a directed graph. Is there a change? No. If you know, why would you do it? It depends. This is maybe more. This is a fancier way of showing things, uh, but you know, you don't actually see the points. That could be a drawback. Anyhow, you could use both of them. And uh, once you have, I'm hoping, and I'm going to make it clear, you're starting to understand what a two-variable relationship is. There are three basic ways to show bivariate relationships, okay? And we use different sort of tables about this. The first one we use is a one-to-one table. It's very simple, okay? We generally do this as columns. I like to do them as columns, but because of space, these are from my notes, by the way. Uh, while you're writing notes, it's simpler to write them in rows instead of columns. But one column will be your one variable, the other column will be your other variable, or in this case, one row will be one variable and the other will be the other variable. And each uh, column, in this case, or each row, if you're writing in columns, would show a single source, a single year, a single person, a single company, whatever. Okay, so if there's a time concept in the data, this would be time one, time two, time three to time n. Or if these are persons or people. I think both are right. Okay, that would be person one, person two, person three, blah, blah, blah. And as an example, for example, you have employment level here and rate of growth of money wages here. And okay, you could just look at this and say, and see probably, okay, as money wages fall, employment rises. There seems to be an inverse proportional relationship. Does it make sense? If you're paying less, then you could hire more people. Or if you have to pay more, then you may maybe want to have a fewer number of people working for you. Not very humane, but nothing is, especially the business life. Right, so that's about it. Nothing much to tell about this one. These are also known as marginal tables, okay? It could be known as one-to-one relationships, one-to-one tables, or marginal tables, or marginal relationships. Both, you could use them interchangeably. Do you have to know them or memorize them? I don't think so. And this is the most frequent thing you're going to be seeing. For example, in one-to-many cases, such as these, now this time you have one variable at the top and the other variable at the bottom. So we generally use this when one variable repeats itself a lot. For example, as you could see, now we have types of companies here and this could be the number of workers in that type of company, or maybe something about those companies. Let's say it's the number of workers, okay? So you collect data from different companies and you see that 2 of them are private ownership companies, personal companies, and 5 of them are limited partnership companies, and you go all to 6 of them are limited liability companies, and 4 of them are joint stocks. That means in a one-way table, okay, or a marginal table, one variable, the y variable, would have many repetitions. So instead of repeating that many times, you could show it like this. You could take one variable here and list the other one below. It could have been the otherwise. If you call the company type X, then X would be your first row, and each Y value, related Y value, would be listed downwards under that X variable, the related X variable. Again, if you think of it, these are tuples. Private ownership, two people working. Private ownership, three people working. Each, if you call these cells, each cell has an y coordinate and an x coordinate. That one, y coordinate, x coordinate. Of course, the data type over here is categorical. This is nominal scales, right? But you could still have a bivariate relationships out of data from different types of scales of measurement, right? You could, here it is. Can you just look at these and say, okay, I see something here, like private ownership companies have very few workers because that's a personal company, okay? While, joint stocks have more workers, or limited liability companies have slightly more workers than private ownership, and then, but there's no direction in this because this is simply nominal. There's no direction, but you could see the differences between different values of the y variable. When y variable changes, then you could expect x variable to change. There's no direction in the y variable here, but still there's a relationship. You could simply say, okay, if you give me a random limited liability company, I expect to have about 15, 16 people, give or take five, for example. Does it make sense? Yes. 15, give five, take five, gets you between 10 and 20, which fits to your data. Or if you give me a random joint stock company, I expect about 23 people working there, give or take three, or give or take two, which satisfies data here. Then you could say, yes, number of people working for limited liability companies and joint stocks are different. Limited partnership and limited liability are different, and joint stock is different, and private ownership is different from all of those, and so on. Okay, this is a one-to-many table, also known as a one-way table. Uh, do we use this a lot? If you need to. Do I? I don't much. And there's many to many. We're going to use this today, and this is very commonly used, okay? And it's where you have one variable as the first row and one variable as the first column, and in between the cells, in the intersecting cells, you get the frequencies, right? First value of the first variable, first value of the second variable, and the intersecting cell is going to be showing you the frequency where x1 is, x variable is x1 and y variable is y1. Like, for example, number of workers in a company. In the age group 18 to 25, there are no directors, because to be a director, you need a little experience. As you could see over here, most of the directors are from 50 to 65 years old, right? There are some from middle-aged group. I'm here, I'm middle-aged, I'm young. You know, in my heart, I belong to this group. In my experience, I would belong to somewhere over there. Okay? But as you could see, there are no very young directors, but there are very young unskilled workers and office workers, and even a couple of foremen. These could be very bright people with not very high levels of education, or could be new graduates from university. We don't know, but as you could see, while the age grows, number of directors increase, number of foremen increase, number of unskilled workers increase to a certain point and then falls, because when you're 50 or 55, it's hard to be an unskilled worker. You probably move to a foreman at that age, because the company doesn't want you to work with your muscles, because that's probably generally what the unskilled workers do. Uh, as a worker who has been unskilled worker for a long time, you know how things are done, so you become a foreman. So you either teach the new guys how to do their job, and you control the other unskilled workers, whether they've been doing their jobs correctly. And office, as age grows, office people also uh, leave their jobs. It seems they could become directors maybe, or move to other jobs. When you see office, this is like, you know, fetch me a cup of coffee, laddie, or will you please take the photocopies of this kind of thing? Not the, no, I'm in an office, I have my own room and desk and that, not that kind of stuff. Okay, this is a many-to-many relationship. So inside here are frequencies, and each, the frequency 4 here means we have 4 people who are between age 25 and 35, and who is also a foreman. Okay, we have 14 people who is aged between 35 and 50 and is an unskilled worker, and so on. Okay, this is very popular, and this is very popular in presenting and analyzing categorical data. Right here, you could see that this is, what scales is this in? Pause and answer. This is in nominal scales, I think. Right? If you didn't have office here, it could have been maybe ordinal scales, unskilled, foreman, director. But there's office here, which doesn't fit with those categories. So this is nominal scales, and this is ratio scales, age. Of course, there's coinciding boundaries here, which you should be, you know, careful with. You know, is 50, age 50 included in this row or that row? You should be, aware of that. But supposing that's taken care of, this is a nice example. So that means, using that many-to-many table, which is known as a cross table or a contingency table, okay, you could analyze nominal data and numerical data together. Generally, when these two come together, you want to group the numerical case, okay, because there are 15 people between age 18 and 25. This could be, 18, 19, 20, 21, 22, 23. There would be one or two of each age probably. And if you take them as single rows, this is uncalculatable. Generally, uh, we don't always obey that rule, but generally, if we have less than 5 as a frequency, we don't like it. So you have 0, 2, 3 here, and you have 0, 1, and so on. What do you want to do? You want to, combine 2 rows or combine 2 columns. In here, can you combine 2 columns? No, because it's in nominal scales. You cannot combine office with unskilled workers, because, being neighbor columns does not mean anything in the nominal scales. You could combine foreman with office if that was possible, or director with unskilled. So we don't do that. Since this is nominal, you're going to leave them as they are. Could you have combined the rows, like for example, have 2 rows, age 35 to 65 and 18 to 35? You could have done that. But then again, you don't want to have too few rows. And even if you combine these 2 rows, you're going to have a frequency of 1 here, and you're going to have a frequency of 1 here. So you cannot get rid of these ones and zeros. So, while you cannot combine them, just leave them as they are. Your analysis would be slightly, less trustable, but sometimes life is like that. You cannot do anything about it, right? Let me have a sip of coffee. And let's go. What's a relationship? I'm going to give it, general description. This is not the textbook description. This is what I feel like it's easier to understand. You're going to have two variables in a bivariate relationship. In a multivariate, it would be three or more. In a univariate, there's no relationship because you're talking about a single variable. So two variables affecting each other. It could sometimes be like that. When you talk about height and weight, generally our consumption is, our perception is this. A taller person would be a heavier person. A shorter person would be a, lighter person. Does it make sense? Yes, generally. Uh, are heavy people taller or are taller people heavier? Sometimes it's not easy to understand which one affects the other one. Sometimes it's easy, sometimes it's not. Or so two variables affecting each other or one affecting the other. This is generally a type of a cause and effect relationship, and we try to denote it like that. This could be like, you know, think about a relationship between exchange rates and interest rates. Generally, interest rates would be the variable that you play around with so that you want to see a response from the exchange rate, right? So sometimes it's clear, or theory, some theory tells you this variable generally affects the other variable, and you try to check whether it's true or not in in your situation, okay, in the country you live in or in the time period that you're interested in, and so on. So two variables affecting each other or one affecting the other in a systematic fashion, okay. So we want this the effect, cause effect, or mutual effect kind of thing to be consistent in a systematic way. By systematic, we mean mathematically analyzable. Has not been a good word, but yeah, that would be it. We should be able to analyze it using some mathematical methodology, and we want to be evident in a certain time period if time is an issue, or we want it to be obvious. So basically you check one variable to guess the other variable. If you go back to that example, okay, if you want to estimate the age of a person, you could ask, what does he do? So if they tell you he's a director, you could say, oh, most probably he must be in his 50s or above. Or I'm sure he's 35 or above, because there's 1/9 probability that he is below 35. Okay, that kind of thing. And it's very similar to the previous probabilities we've been interested in, only the shape changed this time. But if you take a single column and the related rows, okay, it looks like, kind of looks like an ungrouped frequency distribution. And it's the same case about rows this time. If you give me a random person and you say, okay, he's in his 20s yet, not even 25, I would say he's probably an unskilled worker, because 2/3 of that age group work as unskilled workers. So that gives me a chance to look at the age, estimate the position in the company, or look at the position and estimate the age. Sometimes it's easy, sometimes it's not. But life is like that. So you could have a couple of different type of sides in a bivariate relationship. Okay, you're going to have two variables. Both could be categorical, or both could be numerical, or sometimes one would be numerical and one would be categorical. Now, as you have seen just previously, if one is numerical and one is categorical, you could use the categorical analysis type to find the relationship between them. So cross tables, those many-to-many tables or contingency tables, they are the they are the basis for categorical analysis. Okay, when you have nominal data or ordinal data, or both of them, you generally get that cross table with frequencies inside and analyze that to understand whether two variables have any dependency on each other. There's a cause effect relationship with each other. The analysis doesn't tell you which one affects the other one, but it tells you, yes, statistically, we expect a relationship to be here. Then you could, use theory or your instincts to say, okay, that one should be affecting the other one, and so on. So that cross table is the categorical analysis basis. So when you have numerical and categorical, there's other methods for numerical analysis. You cannot do it when you have categorical data. Why? Because when you analyze numerical, remember arithmetic mean, variance, skewness, kurtosis, those kind of parameters, you cannot calculate them for categorical data. Therefore, you cannot uh, use the numerical analysis for categorical data. I sometimes say data, sometimes I say data. Please forgive me. Okay, so that's the idea. If you have two variables, the lesser one defines how you're going to analyze it. But basically, if you have two categorical variables, you're going to do a contingency analysis or cross-table analysis. Okay, that's the best way. With there are exceptions because mostly I'm teaching you one of the two basic roads in analysis, which is the quantitative analysis. Okay, almost everything I teach you is on the quantitative analysis road, and there's also another road which is qualitative analysis, and that is what the social scientists use, psychologists, so socialists, not sociologists, and behavioral scientists, and even in our department, in organizational behavior and more management related type, and even in marketing, they use lots of qualitative analysis, and that's a different world. Okay, you could ask Özge Hoca, Selin Hoca, both Pınar Hocalar, and anyone you see from organization side or marketing side. You could ask them. You could ask Arzu Hoca. They are unbelievably experienced about that type of analysis, and I'm not, right? I'm the quantitative guy. Me, finance people mostly, quantitative analysis people, Barış Hoca, Aydın Hoca, Mustafa Hoca, and we production people, me, Bülent Hoca, Mine Hoca, Hatice Hoca, and so on. And Mehmet Hoca. We are mostly on the quantitative road. So what I'm talking about is the quantitative road, because over there you're going to see, I know some of them. For example, you could try to estimate a categorical variable, and you could use numerical analysis for that, because in numerical, I will say correlation and regression analysis you will use for investigating a numerical to numerical relationship, bivariate relationship. But they have different types of regression, like logistic regression or probabilistic regression, known as logit or probit. One variable over there is, it could be nominal, it could be ordinal, and they use regression analysis to estimate that. There are very bright and clever ways, but we don't get much into that. I'm teaching you the quantitative road. If I had to teach you the qualitative road, I would have to learn it first, and it would take too much time, probably more time than I'm going to teach you the quantitative part. But once you understand the quantitative road, if you want to switch along the way, you're going to be very prepared to understand what's coming. You're going to easily understand what factor analysis is, what logit is, what probit is, what Cronbach alpha is, and so on. They have this whole different literature over there, and it's going to be easy for you to uh, you know get experienced in it. So at some point I had to make this declaration, and it's this declaration. So you're going to learn the quantitative side of the statistics. So if you have categorical variables, both of them, you're going to have a contingency analysis. If you have numerical variables, both of them, you're basically going to use correlation and regression analysis. That could be a linear regression, so you're going to use a straight line, or curvilinear regression, or some other form, which is the nonlinear regression. And you could have a single variable, simple regression, or some different type of many variables, which is known as the multivariate regression. Okay, there are types of it, but the basic idea is the same, and I will make sure you understand that basic idea. And once you understand one regression and correlation analysis, you could easily understand the rest of it. And okay, I will not show you much, but there's also, for the categorical part, not for the nominal, but for the ordinal, there's ordinal regression, and there's ordinal correlation. Ordinal correlation and regression, maybe, if we have time at the end of the semester, remind me, and maybe I could show you how they are done. Numerical categorical, there are two ways here. First one is using the categorical approach to analyze the relationship between those two. And the second one is the statistical inference. All right, that's going to be the whole second semester. And we're going to start. That is where, at this point, you could pause if you like, take a breather. I'll finish my coffee. From this point, we're starting the categorical data analysis. Okay, at this point, you're starting to learn proper statistical analysis. We're going to start with contingency analysis or cross-table analysis. That means we're working with categorical data. All right, so let's first give you the basic idea. Suppose you have 20 candies in a bowl, not as small as these, larger candies, all right? And you have two kids. 10 of these candies are chocolates, 10 of these are fruit flavored, and you have two kids. They're going to share. How do you expect these two kids to share 10 chocolate and 10 fruit flavored candies in a bowl? So, okay, you're young to give that. My son and a friend of my son comes in. I give them a bowl of candies. I don't give candies to my son, but suppose in a parallel universe, deep inside of a parallel. Okay, I give them a bowl of candies. How will they share? Pause, think, answer. Normally, each would get 5 chocolate and 5 fruit flavored, so that they would be sharing equally, right? Normally. Normally means if there is no factor affecting their choices. Now, suppose from the same bowl, one kid likes both types, both chocolate and fruit flavored. The other one goes nuts about chocolate candies, okay? Oh, chocolate candy, chocolate candy. The other one says, oh, I like them both. Now, how will they share? Pause, guess. Presume. Okay. I'm guessing the guy who goes nuts about chocolate candies will get more than 5. Okay, because the other kid will say, okay, I like them both, but I still want to have a couple of chocolate candies, so I will give you 2 chocolate candies if you give me 2 fruit candies. Or maybe if she's a girl, the second kid who likes both, she could say, I will give you 2 chocolate candies if you give me 4 of your fruit candies. And if the other is a boy, he will say, oh yes, I will, and they will share. But if one is crazy for fruit candies and the other is crazy about the chocolate candies, how will they share now? Pose, presume. Probably one will get 10 fruit candies, the other will get 10 chocolate candies. Okay? And there's going to be no fight, and everyone will be very happy. Uh, Now, we don't care about being happy or getting in a quarrel about who's going to get how many. Uh, if the if there's an effect on choice, the natural, expected, obvious allocation is not going to be the case that's going to happen, which means uh, they both should get five chocolate and five fruit, five chocolate and five fruit. I'm the father, and uh, there are two kids fighting over the bowl. I would go and say, okay, what's the problem? Yeah, I want the chocolate candy, more money. Okay, you get five chocolate, five fruit. You get five chocolate, five fruit. Okay, everyone have their candies. You go sit over there. You go sit over there. You could do that, okay? Or you know, if you want to be a better parent, you're going to say, "Oh, let them sort it out." As long as they don't hate each other, they're going to find a way to allocate the candies. But the thing is, if there's something that is not normal, or there's a factor affecting the choice, you would see a distribution that you wouldn't probably expect. Okay, so another couple of examples. These are as the examples. I did these examples before I collected data from you through WhatsApp, and yes, they are stereotyping. And I have had students in the past year saying, "Oh, this is very sexist. How could you say that?" I'm a girl and I like to watch football. What do you mean? And I said, okay, yes, I'm stereotyping because it's very practical to show what I'm trying to show. It's not that I'm sexist or uh, stereotyping person. I'm not. Okay, but it's good to give the example. So 10 people gathered in a house and they don't know what to do. So they said, let's vote. And everybody suggested something and they voted. And watching the soccer game on TV was the one that got the highest votes. Now the question is, did this group have more men in it or more women in it? We're stereotyping process started. Men, because you don't expect if the women were the majority, they wouldn't probably say, "Oh, let's watch the El Clasico. I'm waiting for it for months." There, that could be, but if you take 100 random houses with 10 people in it, where women are the majority, you would get a couple of houses where that happens. Mostly, we expect that if the soccer game won, there would be more men in the house, and it, we're guessing that some of the men would say, "Nah, we're all together. Are we going to watch a game?" And they would be on girls' side, so that I would say, eight men and two women, something like that. Okay, would be my guess. 6 or 7 men said, "Let's watch the game," and one or two guys, you know, they voted for the girls' choice and lost 6-4 or 7-3 or something like that. Another case, 10 people gather in a house, they voted on what to eat. So some said, "Oh, let's have pizza, let's have hamburgers, we could order lahmacun, don't go crazy." And they voted, and pizza won. Should I say pizza, or like a regular Turkish person, or should I call it pizza? Pizza. Do you like some pizza? Okay. Did they have more men or more women since pizza won? Pause. Yes. Presume. I don't know. I don't know. It could be both. They could be equal. It could be all men. It could be all women. 10 women may not have picked pizza, maybe, but I don't know. Could have. We cannot say. We cannot stereotype over pizza. Okay? So 10 people gathered in a house, they voted on what to watch. And this time, the Football World Cup final game was not in the voting list. So the options were, it could be Friends, it could be How I Met Your Mother, and, it could be how Larry met Felly, or how Larry met City, how Mary left Penny. Okay, when Harry met Sally, how I met Sally, how I met your Sally. Okay, those were the alternatives. And oh, do you remember this guy, Octopus Paul? He used to guess the game, so they used many animals to guess the game, and nobody could guess who is going to win better than this octopus. He was quite the guy that you would, ask opinion for betting. And yeah, that game was not in the voting list. They didn't even say, okay, shall we watch the game? Do you think? And how many? What was the majority of the people, men or women? I would say women, probably. Okay, we did our stereotyping, very nice. Okay, and we're done with it. The main idea here is not the stereotyping, but the proportions. What's the probability of a man picking up the or voting for the game? What's the probability of a woman to vote for the game, football game? Or what would be the probability of a woman picking up something else? What's the probability of a man voting for pizza and a woman voting for pizza, and so on? So sometimes you can uh, guesstimate. It's between a guess and an estimation. Okay, you can guesstimate. Sometimes you cannot. When you guesstimate, you have to do stereotyping. Stereotyping as a social means of commenting is not good, but in economics, it's okay. Statistics is about stereotyping data, right? This stock had these returns, so I'm expecting it to get these returns in the upcoming 3 months. So shall I buy that stock or shall I sell it? You're stereotyping the stock, okay? You're looking at the past information and making a guess about how the future would go. Basically, this is the idea. Is everything as expected? If not, is it obvious? You're going to understand what we're talking about, okay? So in a contingency analysis, basically you have inputs, which are the observed frequencies, and you need to find the expected frequencies, and then you're going to compare those to do the analysis, all right? What I mean, suppose I have 100 people in my class, you guys, I didn't ask your uh, opinion about this, so I'm just making it up. I asked, do you like statistics? And 50 people said, yes, I like statistics. And 50 people said, no, I don't like statistics. Okay, I had 50 boys and 50 girls in the class, or men, women, whatever you like. Now I'm asking you, what would you expect? I don't know what I've observed. You don't know what I observed. But what would you expect? How many women would you expect to say yes? How many women do you expect to say no? How many men would you expect to say yes? And how many men would you expect to say no? If you know nothing. Basically, the idea is this. If there are equal number of men and women, and equal number of yes and no's, and if gender has no effect on liking or disliking statistics, you would expect this. Half of the yes and no's in men, sorry, number of yes and no's, frequency of yes and no's in men should be equal. Why? Because number of yes and no's in the whole population is equal. And the number of yes and no's in women should be equal. Why? Because number of yes and no's in the population is equal. Turn it other way around, okay, tilt the graph. I would expect yeses to be equal between men and women because number of men and women are the same in the group, right? And I would expect the same number of no's from men and women because number of men and women in the group are the same. So that is what I would expect. Does this make sense? Why I call this expected frequency, this is the natural way, okay? If gender has no effect on choice. Uh, suppose I teach the statistics course in such a way that boys laugh a lot and have so much fun, but girls are bored and we talk about football all the time and other stuff. All my examples are like that, and girls start to hate me and hate the class. It would be, for example, more men here. 50 boys say yes, and 0 boys say no, and 0 girls say yes, and 50 girls say no. Is this natural? No. Is there an effect of gender on choice in that case? Yes. Boys like it very much. Girls don't like it very much. And we could have, uh, exceptions. Could be, 5 boys say no and 45 boys say yes, and 5 girls say yes and 45 girls say no. Still, would you have said gender has no effect on choice in that case? I would think not. Okay, so but this is a very balanced distribution. The whole thing here is the proportion. The proportion of a variable here is gender. Okay, the proportion of the different values for this variable, if they are the same in every row, and look at the proportion of the choice or the alternatives in the other variable. Do you like statistics? 25, 25, it's proportional with 50, 50. Proportion is 1, proportion is 1, proportion is 1. 20, 25, 25. Okay, if the proportion is the same as the proportions in the totals, okay, then I get the natural distribution of the frequencies. Uh, let's see it with another example. Now, I have 50 boys and 50 girls again, and 40 people said yes, and 60 people said no. What would you expect here? Okay, you could pause and try to fill this in. Pause now, if you will, because I'm going to continue. Now I'm continuing. Uh, the idea is if men and women are equal and gender has no effect on choice, then I expect men and women to have equal proportions in each row, in each decision. Okay, so if there are 40 yeses and boys and girls are equal in number, I expect 20-20 here, 20 men to say yes, 20 women to say no. Then I expect 30 men to say, sorry, 20 men to say yes and 20 women to say yes. And I expect 30 men to say no and 30 women to say no, because there are 60 no's and men and women have the same proportions. Then that equal proportions should be allocated. That 60 should be allocated to these two cells with the proportion here. Or 50 men should be allocated to yes and no's with the proportion of yes and no's. 40% to 60%. 40% of 50 is 20. 60% of 50 is 30. 20-30. Same here, 20-30. And what happened? 20-20, 30-30. All right? So you could take that total and distribute it to these cells. You could have more than 2 cells, by the way. You could have 4, 5, 10, whatever. But the important thing is get this total frequency and distribute it to cells using the proportions of these row totals, or get this row total and distribute it to the cells on the left using the column totals. That's the whole idea. When you do that, you get a case where there is no effect. Having 40 to 60 yes and no's, it's not about breaking the symmetry. Okay, as you could see, this is symmetrical. Nature should not be symmetrical. Okay, you shouldn't always have 50 yeses and 50 no's, or 50 men and 50 women. If we count the people in the class, probably there's going to be, different number of boys and girls. And if I ask, do you like statistics in a closed world, uh, I wouldn't get equal values, probably. Hopefully I would get more yeses than no's. uh, then by looking at them, if I try to estimate how many of the boys said yes and how many of the girls said yes, then I would use this idea. I would use the proportionality. Okay. But in reality, would it be the same? Now, take this case. Make this cell 31. What's going to happen? This is going to be 19 because the total is 50. 31 and 19 should make 50. That one should be 29 and 31 to make this 60, because I cannot change the number of yeses and no's, and I cannot change the number of men and women. All right? I'm just playing with the frequencies. And this would be 21. Now, if that was what I observed, my observation would be slightly different than the expected frequencies, where in here, okay, when you're 20, 20, 30, 30, this is the perfect independence. Gender has no effect on choice, because the men say yes and no with the proportion of the whole population, and women say yes and no with the proportion of the whole population. And the proportion of men and women saying yes and no look very much like each other, 20 to 30, 20 to 30. Okay? And yeses have equal proportions with the proportions of men and women, and no's have the equal proportions as the proportions of men and women in the group. That means it's in a perfect balance. Gender has no effect. Men and women act the same way when making choices. And if you look at the ones who like the class, they're proportional with the total number of boys and girls in the class. And if you look at the people who don't like the course, they're proportional with the number of boys and girls in the course. Perfect balance, perfect independence. There is no effect of gender on choice in this table. If I make this 31, 21, 19, 29, okay, the balance is slightly broken, so that boys like a little less, girls dislike a little more. Okay, so boys who say no is one down. Boys who say yes is one up. Sorry. So the boys like the class a little more, and girls dislike the class a little more. But do you think this is still close to the perfect independent case where we have 20, 20, 30, 30? It's very close, right? Because as I said before, never ever you're going to have that perfect fit. There's going to be slight variations, because you would expect some girls to say no, but they will say yes, and some boys to say yes and they will say no, and vice versa. All right. If I make this 32, 22, now more boys like and more girls dislike, and this would be 18 and 28. So I'm breaking the balance so that this direction, this cross section and that cross section, I'm polarizing that. I'm increasing these two and I'm decreasing these two. 32, 18, 22, 20, 28. Do you think this is still close to the perfect independent case? I would think yes. But let's keep on. This is like putting grains of sand, and you wouldn't notice until it becomes a huge hill of sand. If I make this 34, 20, 33, 23, 34, 24, 35, 25, I could keep these increasing these two as long as the frequency over here lets me. At a point, I could have 50, 0, 40, 10. That would be the maximum polarization I would get. In that case, it would be perfectly dependent, you know. Lots of the only the boys like the course, and most of the girls don't like the course. Okay, then gender has an effect on liking statistics. If it's like this 20, 20, 30, 30, there's no effect. This is the perfect independent case. So as I change those frequencies, there would be such a point that statistics will say, okay, now the change is significant. The polarization is so high that, you know, you should be warned that this is not natural anymore. Gender has started to affect choice. Right. But first, how do we find those? You already understood it. So that 40 will be distributed as 50%, 50%, and that 60 would be distributed as 50%, 50%, or that 50 would be distributed as 40%, 60%, and that one as 40%, 60%. The basic idea is you multiply the row and column total for a cell and then divide it to the total frequency, which means you will take this 40, multiply it with 50, and divide it 100 to get this cell. Why? The cell total of the row total of this cell is 40, the column total of that cell is 50. When you do that, that means you get that 40, and for these two cells, you distribute it as 50%, 50 over 100, 50 over 100, as you see here. This is very simple, right? And very mechanical. Or you could have done it the other way around. You could get that 50 and divide it as 40%, 60%, as you see here. But, you know, the simplest way of doing it would be, you know, finding one cell and then instead of doing these multiplications and divisions, there's an easier way of doing it. Now, this is the formal statistical formulation. It could look, summations and nothing like that, okay? F11, F12, F21, F22. So the first in this I, we call these Fijs, okay? First in this I shows the rows. First row, first cell, first row, first column, first row, second column, second row, first column, second row, second column. So therefore, summation i's will give you column totals, summation over i's will give you column totals, and summation over j's will give you row totals, and double summation of Fij will give you the general idea. So you could formulate it as, take the first row, okay, let me show it like this. Take the first row total, take the first column total, multiply them. In the denominator, always the grand total here, okay? And for the second cell, take the first row total, take the second column total, multiply them, divide the total frequency, and it goes in this fashion, okay? Nothing interesting. So we're going to do a regular example. I imagine I asked you how much you like statistics, okay? And we want to see if gender has an effect on choice. We imagine 57 of the boys said yes, I like statistics, and 35 said no, and 74 of the girls said yes, I like statistics, and 29 said no. All right? Then we have 131 yeses, 64 no's, and I have 92 boys and 103 girls, giving me a total of 195 people. Now I want you to find the expected frequencies here. All right? But to do that, you're going to do this. First, you will imagine there's no frequency inside. You will only take the column totals and row totals. All right? Just get these totals empty here. And then find the expected frequencies. What will you do? Okay, if you want to solve, pause now and solve. What will you do is, you're going to get that 131 multiplied with 92 and divide it to 195 to find this cell. 131 multiplied with 103 divide to 195 to find this cell, and it's going to go in that case. This is a warning, okay? One question, one observed table, one expected table, because, you know, sometimes I give two data sets, two different data sets, Or sometimes I give a single data set and students calculate the analysis for each row or each column. This has been a common mistake. Why I don't know. But for a single cross table, you're going to find a single case, a single expected table, a single analysis, and that's all. And you know, when I did that, I remembered Freddie, the song One Vision. It goes on like one question, one observed table, one expected table. Okay, so you're going to calculate this. Multiply row and column totals divided to total frequency, and that's how it goes. This is the way you calculate it. I won't spend too much time on that. You could do the calculations and go on. Now, okay, you could have more decimal places here, but I think 0.1 decimal place is enough for us. It changes your calculation slightly, but that's not a problem. You could round up until you have 1 decimal after the dot. So this is what we have. This is our expected table. 61 point, almost 62, 69, 30, 34. Let's go back to see. 57, 35, 74, 29. This is not bad, okay? This looks close, so the observed and expected frequencies close to each other. But are they close enough so that we could statistically say there's no effect of gender on choice? But before that, instead of doing all these individually, I will show you the quick way of doing things now. If you calculate one cell, you don't have to do 131 times 103 divided by 195 here. If this is correct, to find this cell, you could just subtract 61.8 from 131 and you find this cell. And you could subtract 61.8 from 92 to find this cell. And either then you could use that and 64 to find that, or that one and 103 to find that. So you should just calculate that, and these other three will be calculated as a simple subtraction. All right, and that brings you to the concept of degrees of freedom. Okay, we have, I think, talked about degrees of freedom, maybe in a live question answer session. Maybe you may want to go and watch those if you already haven't. A cross table has always a degrees of freedom, and the degrees of freedom is much clearer in a cross table. Now, imagine you had a blank table, okay, something like that. And I want to fill it the way I like. Can you fill it the way you like? Let's see what you could do. I want this cell to be 15. Can I make it 15? Yes. Okay. Let this be 15. I'm free to pick the value of this cell. Am I free to pick the value of this cell now? No, it has to be 92 minus 15. I'm not free to choose this. And I'm not free to choose this. It has to be 131 minus 15. And now I have 3 cells full. I just picked one. And I'm not free to pick that. This would be 64 minus 92 plus 15, whatever that is. Right? Yes. That would be the case. So in a 2x2 table, 2x2 cross table, I'm only free to pick one cell. The idea is, whatever dimensions of your table, you should delete one row and one column, preferably the last row and the last column, and the remaining number of cells will be your degrees of freedom. It's going to be clearer in the upcoming examples, okay? But this is important. You should know how you find the degrees of freedom in a cross table, okay? If it's a 2 by 2, this is a 2 by 2 table. You don't care about the names of the variables or totals. We don't care about those. The inside of the table is the important part. This is a 2 by 2 table. Delete the last row, delete the last column. You're left with a single cell. Okay, that brings you to the concept of degrees of freedom. It's going to be important and it's going to be useful. Now, we are almost halfway to our analysis to give the answer to does gender affect choice of liking statistics. Okay, what we have done is we found the expected table. So observed table, expected table. This is the starting part. Now we're going to do the formal analysis, and the question is going to change slightly. Now the real question would look like this. We collected data from our class at a 95% confidence level, which, okay, we should maybe make this clear. That means if I repeat this analysis 100 times, I want to have the same outcome 95 times, the same result, okay? So I want to be 95% sure of my answer. For example, I could ask you my weight and you could guess a value, and I would ask, how sure are you? You could say, for example, I'm sure 10%, 30%, 50%, 90%. To give me a larger percent, you have to use a larger interval. For example, if you say you should be between 0 and 500 kilos, then you would be 100% sure, but the interval would be too large. Or you could say you're from 50 to 150, you would be 99.999% sure with a smaller interval. Or you could say you must be 70 to 110. Now you could be 95% sure, and so on. This confidence level thing is going to be clearer more in the second semester when we talk about statistical inference. For the moment, just take it as a given, fixed way of doing things. All right? So it's the probability that we trust our conclusion, right? I will talk more about it if necessary, but for the moment, I think that should be enough. This is like an industry standard for statistics, 95%. We're going to test whether gender has an effect on liking or disliking statistics. The solution procedure is going to be like this. You're going to first find the expected table, okay? Then I will ask you to write down your hypothesis. In generally, most of the analysis that you will come up to, you're going to have a set of hypotheses. One will be a null hypothesis that we show with HO generally, or sometimes H0. That would be your null hypothesis. It's going to look like this. The null and every analysis method has its own hypothesis approach. The contingency analysis has this null hypothesis. Liking or disliking statistics is independent of gender. So in a contingency analysis or cross-table analysis, your null hypothesis always suggests independence. So if you, based on your conclusion, you're going to say, okay, I pick HO, therefore I guess with a 95% probability, I think gender has no effect on liking statistics. They're in the two variables are independent. And you're going to have, against HO, there's going to be a fitting other part, which would be the alternative hypothesis. It's going to say, no, dude, it's dependent. Okay? Your null hypothesis says independent. Your alternative hypothesis says it's dependent. It's going to become clearer today, I promise you. All right? But this is the case. Always independent in the null hypothesis and always dependent in the alternative hypothesis. So you write down your hypothesis, then you will need a test statistic to calculate. This is you're going to look at the statistic, and it's going to you're going to compare it with a table value, and it's going to say, okay, they're independent, or no, they're dependent on each other. Your test statistic has this name. This is not an X, by the way. You could notice the shape. It's the Greek letter chi, CHI, okay? This is the chi letter, okay? And this is a calculated chi-square or chi-square calculated. This is the name of your variable, all right? You should be familiar, you will become familiar with this notation. Basically, it's a double summation over ij, which means in your table, for every cell, you're going to find the difference between the observed and expected frequencies, then square it and divide it to the expected frequency. If you didn't have this square, a value minus another value divided by the second value, you should be familiar with this. It's the rate, it's the change, rate of change, right? In calculus words, it's the rate of change. But in a cross table, you cannot just find that rate of change. What's going on? Okay, and why can't you just do a simple rate of change? Suppose I give a simple question, whatever that is. I have 20 boys, 20 girls, 20 yeses, 20 nos. In the expected case, equal number of men and women and equal number of yes and nos. That means 20 times 20 over 40. I have 10, 10, 10, 10. Okay, this is my expected table. In reality, I have seen 5 yeses and 15 nos from men and 5 nos and 15 yeses from women. What do you, off topic, what do you think of this? Is this close to that one? Do you think there's an effect of gender on choice here? I think there is. But suppose we do not take the square, but we calculate the rate of change for every cell and then sum them up. What's going to happen? We're going to have 5 minus 10. Okay, take the observed here. Go to the same cell in the expected table. 5 minus 10 divided by 10. So you're going to have a minus 5 over 10. Second cell, 15 minus 10 divided by 10. You're going to have a plus 5 over 10. Go to the third cell. Take this 15 minus 10 over 10. Another plus 5 minus 5 over 10. And last cell, 5 minus 10 over 10. And another minus 5 over 10. If you sum these up, you get 0. I use a 2 by 2 cross table because it shows you many things. For example, it shows you this. In a balanced cross table, 2 by 2 cross table, you're always going to get 0 if you calculate those rate of changes and sum them up. That's why you get the square, to get rid of these plus minus values canceling each other, right? So if you square them, it's going to be squares of these summed up. 25 over 10, 25 over 10, 25 over 10, 25 over 10, which is going to be a 10, right? So that's why we squared this guy. It's very similar to why we squared the variance while calculating it. Okay, so this is the squared rate of change summed up for each cell, not for each row, not for each column, but for whole of the table. So when you calculate that, you're going to compare your statistic with a table. This table here is a chi-square table, okay? It's a table that is documented already. I will share it with you in Evdekal, and I will show a portion of it today in the lecture. And you use that table to find the value, and I will describe what that value is. Just hold your horses. I will make everything clear for you. Okay, then you make your conclusion. If your calculated value is smaller than table, you pick HO. You say, I cannot reject HO. They should be, they look independent. If your calculated chi-square is larger than the table value, chi-square table value, then you say, I reject HO. Alternative hypothesis must be true. They are depending on each other. And as last week, as I told you, when you reject, you're more confident, because when you do not reject, when you say, okay, HO must be true, they look independent, it happens 95% of the times with a similar data set. Okay, so but when you reject, either you have to be very unlucky because they're actually independent, but you had such a data set that lets you say, okay, reject, they look dependent, or actually they are dependent. Okay, that's one of the two alternatives. And when we reject, we don't think I should be very unlucky so that the data mislead me or misled me. Okay, I say if I reject, then I reject. They are dependent. That data does not show any sign of independence here. But when you do not reject, when you pick HO, you don't say, oh, they are independent. You say, they look independent. I cannot say they are dependent. Okay? So I fail to reject HO. You do not say, I accept HO. I accept the null hypothesis. These are going to be clearer, and you're going to get used to it in a couple of minutes. Let's get back to the question. So uh, a formal solution to a contingency analysis will look like this. You will write down your hypothesis first. Null hypothesis, liking or disliking statistics is independent of gender. An alternative hypothesis will say, no, dude, it's dependent, or they are dependent. But here, it's dependent. Then you calculate your test statistic. Okay, you have to go back, remember the observed frequency table and expected frequency table, and match cell by cell those tables and calculate the squared difference for each of them. So 57 was the first cell, and 61.8 was the observed frequency corresponding to that cell. Take the difference, square it up, divide it to the expected frequency. Second cell, observed minus expected. Take the square, divide it to the expected. Divided to the expected is critical here because the difference and the fact that you square the difference, it doesn't matter. It could have been expected minus observed squared. It would give you the same thing. But the denominator is always expected. That's the important point you have to understand, because that's how you find the rate of change, right? That is your standpoint. The perfect independent frequencies is your standpoint to understand if data behaves independently or dependently. Now, the main idea, while you see this calculation, is this. If the observed frequency and the expected frequency are very close, this would be a small number, and the square of it will also be a small number. And when you divide it to the expected frequency, that's going to be a small number. And if you sum up four small numbers, then you would have a very small chi-square calculated value. If your calculated chi-square is very close to zero, that means your data set acts like the expected frequency table, which is perfectly independent. But if the differences are high between the observed and the expected, this distance, the difference would be a larger number, square of it will be squarely larger, and that division will give you a relatively larger number. And if you sum up four larger numbers, then you would have a large chi-square. So as chi-square calculated grows, you move from independence to dependence. As chi-square approaches to zero, you move from dependence to independence. And if it gets very close to zero, you move to perfect independence, no effect of the two variables affecting each other or one affecting the other one, okay? For example, if you had, instead of 57, if you had 62 here, you would have 0.2 squared, which is 0.04, divided to 61, a number very close to zero. For example, 30.2 squared 0.04 divided by that. Again, a small number. So if you had 62, 30, 70, and 34, you would find a chi-square which was almost zero. And would you say they're independent? Yes, because observed table and the expected table would be almost same, just rounded up. That would be the perfect independent case. Gender has no effect on choice, or variable one has no effect on variable two, variable two has no effect on variable one. But you have relatively larger numbers here. This is like 5 squared, 25 over 61 would give you 0.4-ish, and 25 square over 30 would give you 0.8-ish. Still not large numbers. 1.3, you're going to see. 2.16 was the case. Your calculated chi-square is 2.16. In a perfect independent case, it would have been 0. In a perfect or highly dependent case, what would it be? We don't know. Uh, but we have the chi-square table so that we can compare. That means chi-square table tells you uh, the largest possible value for the chi-square calculated so that you could accept or fail to reject this null hypothesis. So you would comment, they look independent. Or if your chi-square calculated is larger than that table value, you're going to switch to the alternative hypothesis and say they are dependent. One affects the other. I don't know which one affects the other one, but one affects the other one. So we're going to learn how to compare this chi-square table, chi-square calculated with the chi-square table. In order to do that, you're going to have your tables in EVDECAL once again. I will give you the table that I'm using here in the presentation. But that table has two inputs, one probability, the other degrees of freedom. So the probability is what the question gives us, 95% confidence, it said. So keep that in mind, okay? And we're going to input degrees of freedom. As you remember, this is a 2 by 2 table and your degrees of freedom is 1. So that's your table, okay? It has a graph here. This is the graph of a chi-square distribution. It starts from 0 generally. It's squared, so it's not negative. Okay, tables sometimes give the left-hand side probability, sometimes give the tail probability or the right-hand side probability. This table denotes the right-hand side probability with an alpha. Now, we want to be close to 0 if we are independent in our table. So this is the fail to reject part for us. So that's the confidence level. And the table gives the rejection probability, which we call as the significance level or significance probability. That means we have 95% here, we have 5% over there. There's a 5% chance that we will reject a true null hypothesis, or actually they are dependent. We do a correct job of rejecting. These are going to become, again, clearer in the second semester, but maybe if needed, I will spend another week to make you understand the logic behind this. But first learn the mechanics of this. 95% confidence is here, so 5% significance is there. So I go and pick 5%, 0.05. So the chi-square value I'm looking for is in this column, and I find the degrees of freedom that I'm interested in, 1. So the first value of this column, 384, would be my chi-square value. So the table tells me if your calculated chi-square is less than or equal to 3.84, then you have a relatively small chi-square value, which means the observed and expected frequencies in your table are statistically close enough to each other so that you could say there's no dependence. Okay, I picked that 384 with 0.5 probability, right-hand side probability. 95% that I'm given is on the left. I take this. Oh, it would be the terrible mistake if you go to 0.95 because it gives you 0 here. Okay, let that be a warning for you. You're always going to look at the right tail, and that's the probability you're looking for, and that's the chi-square you're looking for. I will go back. This is my calculated chi-square. This is my table chi-square, and I will. And if this is the case, okay, if calculated chi-square is smaller or equal to 384, I will say, okay, I pick HO. Otherwise, I pick HA. Is it smaller? Yes, it's smaller. Graphically, this is what happens. This is my chi-square distribution. The table gives me 384, and if this chi-square value is closer from this table value to the zero side, I will say, yeah, they look independent. If it's on the other side, I will say, oh, that's a big chi-square. It's larger than what the table expects. Then the the observed and expected frequencies are far away from each other. That means, they're dependent. This is not natural. Something affected. Probably gender affected the choice. Okay? So you reject. If you reject what? Reject HO. Always fail to reject or accept, if you will. But fail to reject is the better term. Fail to reject this HO or reject HO. You make your decision based on HO. You could say, if you're rejecting this, you could say, okay, I pick HA, but doesn't matter. Then my calculated chi-square is here. It's not in the rejection zone, therefore I cannot reject HO. This is the nice words of saying it. I cannot reject HO. When I reject, I'm more confident. When I fail to reject, I fail to reject. I'm not very confident, but that's what the data tells me. So you say fail to reject HO. Gender has no effect on choice. Better to say it looks like gender has no effect on choice. Okay. So a couple of final examples, three examples in a row. This is the data from you. It's a little judgmental or stereotyping again, but I wanted to see what happens because in the past years I asked the students, would you like to watch a football game? Boys would heavily say yes, and girls would heavily say no. And I would ask, uh, okay, we have spare time. Shall we go to a shopping mall? Walk around the shops and so on. And the girls would heavily say yes, and boys would heavily say no. And I would ask about spinach or cereal or okra or whatever, and I would find no effect of gender on liking a certain kind of meal. What's going to happen with you? Okay, effect of gender on watching football was one of them. This is the stands of the Cork City Football Club, uh, Turner's Cross Stadium. These guys are known as the Rebel Army. I was in those stands, cheering with those guys. Uh, Effect of gender on shopping and effect of gender on eating spinach. Right? I'm Popeye the Sailor Man. We collected data from WhatsApp and we're going to see how it turned out. Your preliminary expectation, what do you think before seeing anything? Do you think being a boy or a girl affects your choice on picking a football match as a pastime if you have a spare time, a couple of hours free time? Our prejudices have been teaching us that if you're a boy you're more likely to do it, if you're a girl you're less likely to do it. But is it the case? So out of your answers, I'm hoping I didn't make a mistake here. So the messages are in the WhatsApp over there, so you could recount if you like. I could have one or two errors, but 36 of the boys said yes, I'd like to watch a soccer game, and 10 boys said no. Interestingly, girls are almost equal in picking yes and no. Even half, more than half of the girls said yes, I'd like to watch a soccer game, and 20 of them said no. Now, there's a couple of things that you could be looking at. Number of yeses and number of nos. Look at the ratio here. Almost twice are the frequencies of yeses, total yeses. So what do you expect? Two-thirds for perfect independence. What do you expect? Two-thirds of the total people say yes. One-third of the total people say no. So out of this 46 people for a perfect independence, I expect two-thirds of this, about 30 to 31 to say yes, and 14, 15 of them to say no. Are they close? Yes. About these 41, make it 42. I would expect um, 28, 29 to say yes, and the rest to say no. But here the frequency of the girls saying yes is relatively lower. So I could imagine, as a statistician, I could imagine this table is going to give me a reject. It's going to say yes, gender is dependent on this choice, even though girls, you know, show the incredibly high frequency of saying yes. Still, the yeses are dominated by the boys. If you think these frequencies are almost equal, you would expect also equal frequencies of no's from boys and girls and yeses from boys and girls. But the boys are almost twice as more as girls still, even though they should be slightly higher. And in no's, girls are twice as higher as boys, whereas we would expect almost equal and or a little higher frequency of boys to say yes. My preliminary expectation would be this. This is going to be a reject HO. Gender has an effect on choice. They are dependent, but we're going to see what's going to happen. Okay, that's my first impression. So we're going to go analyzing this. We're first going to get the expected frequencies. Uh, you could stop, calculate, and check, because I will not spend time on showing. Multiply those guys, divide that to 87, find that, subtract, 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 find the ungrouped frequency table. And then you're going to calculate the test statistic. Let's do this formally. First, write down your hypothesis. Willing to watch a football game in your spare time. It is independent of gender for, Hacettepe University Business Administration first year students. I should also tell what my population is. Alternatively, no, it's dependent. So if I fail to reject, I will say independent. If I reject HO, I will say they are dependent. I think they will be dependent, but we're going to find out. Observed minus expected frequencies squared up divided to expected frequencies. And I will, for the last time, I show this calculation. Okay, from now on, I will just give you the top, the outcomes, and we're going to see. So you could just look at this 6 36 divided by 30. This is 1 plus something. And remember, our table is still 2 by 2. So our chi-square table value will still be 3.84. We're going to compare this chi-square calculated with that 384 because it's the same degrees of freedom. And we're again testing at the 95% confidence level. So the table value doesn't change. And interestingly, if you have a 2 by 2 table, your numerators are always the same. Don't spend time calculating once again. Now see, 5.9 squared, 5.9 squared, 5.9 squared, 5.9 squared. If it's more than 2 by 2, 2 by 3, 3 by 2, 3 by 3, this changes. But in a 2 by 2 table, numerators are always the same. The denominator changes because of that balance thing I showed you, 5, 10, 15, 10 kind of thing. Okay, so let's call it 36 roughly over 30, 1.23 something. 36 over 15, this is 2, more than 2, almost. And 36 over 14, this is more than 2 again. So I got more than 2, more than 2, 1-ish, and slightly more than 1-ish. I got 6, more than 6. So obviously this is a large chi-square. It's 7.02, okay? Compare with the table. You're going to compare this with 3.84. Is it equal? No, it's not equal or smaller. Then your comment is going to be reject. Reject HO. Reject the fact that they are independent. They depend on gender. Okay, graphically, that's your rejection region. That's your critical table value. This is sometimes given as chi-square table, sometimes given as chi-square critical. Sometimes you directly write the probability and the degrees of freedom here so that it shows that it's a table value. I will show how that is written in a few minutes. Okay, reject if it's on the right hand side. If you're closer to 0, they're independent. If you're outside of the table value, then they're dependent. Okay, 702 is there. Rejected fear, yes, that's a rejection. You reject HO. Watching football depends on gender for this group of students. I'm not saying when when I accept HO, I don't say I accept HO. They're independent. I say, okay, I don't have enough evidence to say they are dependent. They look independent. I fail to reject. But when I say reject, I reject. Okay, they are dependent. End of the story. Knocked out. Okay, second case, gender on shopping. Again, what's your preliminary expectation? You expect girls to spend more time on malls because this is again very stereotyping, but uh, boys generally don't like to hang around and walk around. We all have uh, many times for our girlfriends or for our wives, for our mothers at times, but we don't like doing that much generally. That was at least what I thought until seeing that data set. Boys said 30 to 16, they said yes, and girls said 33 to 8, they said yes. Now, look at the totals again 63 yeses, 24 no's. Uh, Almost twice as high, little slightly more higher than two times. So again, you could roughly say two-thirds, one-third. Uh, and look at the boys, two-thirds, one-third. Perfectly proportional, almost perfect. If this was 14, 13, it would be perfectly proportional, but this is very good. And girls, even though yeses are a little dominating, there are enough number of eights to say the proportionality is not very bad. And if you consider these as almost equal frequencies, almost equals in yeses, slightly higher we have boys in no, but I estimate this to be a fail to reject. The proportionality in this table seems very nice. And probably this is going to be the first time in my life when shopping malls will be rejected, is failed to reject it. Now we're going to see. Let's get the expected frequencies. 33, 29, 12, 7 to 11. Remember 30, 33. This was 30, this was 33, 14 and 8 or something like that, 16 and 8. Very close. I think this would be a close race. So write down your hypothesis. Willing to go to a shopping mall in the spare time is independent of gender for our class. Alternatively, we're going to say it is dependent. Your test statistic, I'm not calculating in detail. You do it for yourselves. 2.53. We already know that this is a fail to reject because the test statistic does not change. Let's see. Is it smaller or equal? Yes, it's smaller or equal. Test verified. So your comment is going to be it's not in the rejection zone, it's closer to zero. So fail to reject HO. Going to a mall is independent of gender for our class. First time in history, you're rewriting history. And that frequency on watching football for girls, again, first time in history. It was a reject, but it was pretty close. If I admit, I used to get chi-squares like 12, 15, some large polarization before. And gender on spinach. Do you think your genders affect whether you like to eat or not eat spinach? In the past, it has always been, gender has no effect on liking a certain type of food. I especially pick spinach, okra, cereal, that kind of thing, so that I get independence. But look at this. Look at this. This is crazy. Boys are polarized on saying no, and girls, not dominatingly but largely say yes. So the 35 yeses are mostly from girls, and 33 no's, uh, where the total is 52, are from boys. So this is where your table is polarized. in cross terms, this is easily going to be a rejection. It's the first time I will ever see, girls tending more to like spinach and boys not liking spinach. And I will have a couple of comments about this in the live session if you remind me to tell. Uh, this is incredible. There could be a couple of reasons why this happens. Not this, but again with the other ones. Let's quickly calculate. This is our expected table, okay? And hypothesis. Chi-square 582. We already know we rejected, right? Because it's still 384. Is it smaller? No. Then reject HO. Gender has an effect on liking spinach in this class. Girls like it more, boys like it. Yes. You prince, have you been brought as prince boys? Prince boys. I don't like spinach. Oh, my dear son, I hear köfte for you, macaroni for you. When girls say, I don't like spinach, you have to eat. It's good for you. Eat it, my girl. And uh, maybe it's something like that. Okay, last example for today. I think this has been quite long again, but what can you do? Let's make some data up about an imaginary company. So we have this company, and these are the workers in the company. These are the education levels, ordinal data, right? Primary school, high school, university, master's, PhD degree. And these are the wages, monthly wages of that company. Less than 3,000, 3,000, 5,000, 5,000, 10,000, and more than 10,000, okay? And 265 people were working in this company. And this is the distribution. 95 people who were primary school graduates earn less than 3,000, and it goes on like that. Okay, uh, we're going to check if education level has an effect on incomes within this company. Right. This is the expected frequency table. You just calculate it. This time it's a more work of calculation, and you have to calculate this, this, and this to find that. You could find the last one by subtraction. This, find by subtraction. This, find by subtraction. Subtraction, 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 subtraction. In the end, close this column, close this line, and the remaining number of cells will give you the degrees of freedom. So expected frequency is here, and we're going to find the, okay, first write down the hypothesis. Incomes depend on education level in this company, or, oh, this is wrong. Just a moment. I think I had become tired. Incomes do not depend on education level will be your null hypothesis. Let me save that. In a minute, I'll be with you. Again, okay. Share screen, left one. Okay. Oh. Okay. Incomes do not depend on education level. No, they do. Okay, I would change that again, but not now. Calculate your test statistic, and you're going to get 212. Now, you should have a very large chi-square table value in order to fail to reject that, but it looks like you're going to fail to reject that, okay? So you need a table value. This is how you also formally show the table value. 95% confidence will return to you as 5% significance level, the remaining portion, and 9 degrees of freedom. From the table, it's 16.92. Is it smaller? No, it's not. Then yes, in this company, they depend. But see the degrees of freedom first. You close this last row, the ones, and you close down this last column, okay? The remaining cells will be your degrees of freedom. 1, 2, 3, 4, 5, 6, 7, 8, 9. The ones you can calculate by subtraction, the ones you cannot calculate by subtraction. Ones you cannot calculate by subtraction will be your degrees of freedom. But in a cross table, it's easy to find row minus 1 times column minus 1. You had 4 rows minus 1, 3. You had 4 columns minus 1 will be 3. 3 times 3 is going to be 9, which is the number of cells in this rectangle here. Okay. And from your table, again, confidence level 95, table gives you the tail probability. So 1 minus 95% will be your 5%. And 9 degrees of freedom, you go down there and you pick 16.92. Okay. So if your calculated chi-square is equal or smaller than 16.92, you're going to fail to reject. You're going to say, in this company, incomes do not depend on education level. But if it's higher, then you say, I reject, incomes depend on income level, education level. Okay, so graphically, that's your rejection line, and that's your calculated chi-square. It's a clear rejection of the null hypothesis. So you say incomes depend on education in this company. And that's it. Yeah. I hope it's been a nice. I can't see how long it has been. An hour and a half, close to 2 maybe. What can I do? You know, when you got to do what you got to do. You may have questions about this. You know, save them for the live question and answer session. If you don't attend the live question and answer session, please do. Otherwise, you know, the links are in Evdekal. Go back and watch them before asking me a question. Now, I welcome all questions and I appreciate all people who tend to ask questions, but if you keep on repeating questions that I've answered in the live sessions, that means you're not watching them. That means you're not interested in others people's questions. That means I'm not interested in answering your questions. Okay, watch them, and if you do not find your answers there, then come and ask me. Right? I think this would be a fairer way of doing things. So, thanks. Take care. I'll see you tomorrow morning live and in video next week. Okay?